To be adequately prepared for a journeyman's test, aim for a score of at least 80 to 85% on practice tests. This score range indicates a strong understanding of the material and increases the likelihood of success in the actual exam. In addition to National Electrical Code Table 314.16, there are several resources available to find box sizes for box fill calculations. Firstly, consult National Electrical Code Annex D, which provides information on box fill calculations for various types of enclosures. Secondly, Underwriters Laboratories, or UL, publishes standards for electrical enclosures that specify box sizes and dimensions, so checking UL standards is recommended. Thirdly, manufacturers of electrical boxes and enclosures typically provide box dimensions in their catalogs. Reviewing these manufacturer catalogs will provide specific dimensions for various box types. There are also online calculators available that can help determine box fill based on the number and size of conductors in the box. Box fill calculations are a critical aspect of electrical installations, ensuring safety and compliance with the National Electrical Code. The National Electrical Code specifies requirements for the maximum number of conductors, devices, and fittings allowed in electrical boxes. These requirements are designed to prevent overheating and damage to conductors, which can lead to electrical hazards. To accurately calculate box fill, one must consider several factors including the size and number of conductors, the number of devices such as switches and receptacles, and the presence of fittings such as internal cable clamps or support fittings. Firstly, the size and number of conductors are the most fundamental factors in box fill calculations. Each conductor entering the box contributes to the total fill volume, with larger conductors occupying more space. The National Electrical Code provides specific fill values for different conductor sizes, as outlined in Table 314.16. These values represent the volume occupied by each conductor in the box. Secondly, devices such as switches, receptacles, and equipment grounding conductors also contribute to the box fill. The National Electrical Code considers each device to be equivalent to 1 or 2 conductors, depending on their size and type. For example, a single switch or receptacle is typically counted as 2 conductors, while a grounding conductor may be counted as 1 conductor. Thirdly, fittings within the box, such as internal cable clamps, support fittings, or hickeys, must also be accounted for in the box fill calculation. The National Electrical Code specifies fill allowances for these fittings, which are added to the total fill volume. The calculation involves adding the fill volume of all conductors, devices, and fittings in the box and comparing it to the maximum allowable fill volume for that box size. If the total fill volume exceeds the maximum allowable volume, a larger box must be used. The National Electrical Code provides tables and guidelines for determining the appropriate box size based on the number and size of conductors, devices, and fittings. Understanding the National Electrical Code requirements for box fill calculations is essential for ensuring safe and compliant electrical installations. Overfilled boxes can lead to overheating, conductor damage, and potential fire hazards. By carefully calculating the box fill and selecting the appropriate box size, electricians can prevent these hazards and ensure the long-term reliability of electrical systems. In addition to the basic principles of box fill calculations, there are several advanced considerations to keep in mind. Firstly, when conductors of different sizes are present in the same box, the fill volume must be calculated based on the largest conductor size. This ensures that the box is adequately sized to accommodate all conductors without overcrowding. Secondly, when conductors are spliced or terminated within the box, the fill volume must include the space occupied by the splices or terminations. The National Electrical Code provides specific guidelines for calculating the fill volume of splices and terminations, depending on their size and type. Thirdly, when non-metallic boxes are used, special considerations apply to the fill volume. Non-metallic boxes are typically smaller than metallic boxes and have lower fill volume allowances. The National Electrical Code provides specific requirements for box fill in non-metallic boxes. It is important to consult these requirements when working with non-metallic boxes. In summary, box fill calculations are a critical aspect of electrical installations, requiring careful consideration of conductor size, device count, fitting allowances, and box type. By following the National Electrical Code guidelines and understanding the advanced considerations, electricians can ensure safe and compliant installations that prevent electrical hazards and ensure the long-term reliability of electrical systems. Always consult the latest edition of the National Electrical Code for the most up-to-date information and requirements. The National Electrical Code is updated regularly to reflect changes in technology and best practices. Staying current with the National Electrical Code is essential for all electrical professionals. The minimum bending radius for conductors is another crucial aspect of electrical installations, ensuring the integrity and longevity of wiring systems. Bending conductors too sharply can damage the insulation, reduce current carrying capacity, and create potential safety hazards. The National Electrical Code, or NEC, provides guidelines and requirements for minimum bending radii based on conductor size, insulation type, and installation method. Understanding and adhering to these requirements is essential for all electricians and electrical contractors. The minimum bending radius is the smallest radius to which a conductor can be bent without damaging its insulation or impairing its electrical performance. This radius is typically expressed in terms of the conductor's diameter or circular mil area. The National Electrical Code specifies minimum bending radii for various types of conductors, including copper, aluminum, and copper-clad aluminum. These requirements are found in Article 300.34 and Chapter 9 tables. Firstly, conductor size is a primary factor in determining the minimum bending radius. Larger conductors generally require larger bending radii to prevent damage to their insulation. The National Electrical Code provides tables that list the minimum bending radii for different conductor sizes based on their insulation type and voltage rating. Secondly, insulation type also affects the minimum bending radius. Different insulation materials have varying degrees of flexibility and resistance to bending stress. The National Electrical Code specifies different bending radii for conductors with different insulation types, such as THHN, THW, and XHHW. Thirdly, the installation method can also influence the minimum bending radius. Conductors installed in raceways, such as conduits or cable trays, may have different bending radius requirements than conductors installed in free air. The National Electrical Code provides specific guidelines for bending conductors in different installation scenarios. Bending conductors properly is essential for maintaining the integrity of electrical systems. Sharp bends can cause the insulation to crack or tear, exposing the conductor to moisture, corrosion, and potential short circuits. Damaged insulation can also reduce the conductor's current carrying capacity, leading to overheating and fire hazards. To ensure proper bending, electricians should use appropriate bending tools and techniques. These tools help to create smooth, uniform bends without damaging the conductor or its insulation. Hand benders, conduit benders, and cable benders are commonly used for bending conductors of various sizes and types. When bending conductors, it is important to avoid kinking or flattening the conductor. Kinks and flats can create stress points that weaken the conductor and make it more susceptible to damage. It is also important to avoid overbending the conductor, as this can stretch or deform the insulation. In addition to following the National Electrical Code requirements for minimum bending radii, electricians should also consider the physical constraints of the installation environment. In tight spaces, it may be necessary to use larger radius bends to avoid obstructions or maintain clearance. In some cases, it may be necessary to use factory-made bends or elbows to achieve the desired bend radius. In summary, the minimum bending radius for conductors is a critical aspect of electrical installations, ensuring the integrity and longevity of wiring systems. By following the National Electrical Code requirements and using proper bending techniques, electricians can prevent damage to conductors, reduce the risk of electrical hazards, and ensure the safe and reliable operation of electrical systems. Always consult the latest edition of the National Electrical Code for the most up-to-date information and requirements. The National Electrical Code is updated regularly to reflect changes in technology and best practices. Staying current with the National Electrical Code is essential for all electrical professionals. Furthermore, it's essential to understand the concept of ampacity, which is the current carrying capacity of a conductor. Ampacity is the maximum amount of electrical current a conductor can carry continuously without exceeding its temperature rating. Several factors influence a conductor's ampacity, including its size, insulation type, installation method, and ambient temperature. The National Electrical Code, or NEC, provides tables and guidelines for determining the ampacity of various conductors under different conditions. Understanding and applying these guidelines is crucial for ensuring the safe and reliable operation of electrical systems. Firstly, conductor size is a primary determinant of ampacity. Larger conductors have a greater cross-sectional area, allowing them to carry more current without overheating. The National Electrical Code provides ampacity tables that list the allowable ampacities for different conductor sizes based on their insulation type and temperature rating. Secondly, insulation type also affects ampacity. Different insulation materials have varying degrees of heat resistance. Conductors with high temperature ratings can carry more current than conductors with lower temperature ratings. The National Electrical Code specifies ampacity ratings for conductors with different insulation types, such as THHN, THW, and XHHW. Thirdly, the installation method can also influence ampacity. Conductors installed in free air can dissipate heat more effectively than conductors installed in raceways or cable trays. The National Electrical Code provides different ampacity ratings for conductors installed in different configurations. Ambient temperature is another critical factor affecting ampacity. Higher ambient temperatures reduce a conductor's ability to dissipate heat, lowering its ampacity. The National Electrical Code requires ampacity adjustments for conductors installed in high-temperature environments. These adjustments are based on the conductor's temperature rating and the ambient temperature. To determine the appropriate conductor size for a given application, it is essential to calculate the load current and apply the appropriate ampacity correction and adjustment factors. The load current is the amount of current that the conductor is expected to carry continuously. The ampacity correction factor is used to adjust the ampacity for ambient temperature, while the ampacity adjustment factor is used to adjust the ampacity for the number of conductors in a raceway or cable tray. The National Electrical Code provides detailed guidelines for calculating load currents, ampacity correction factors, and ampacity adjustment factors. Understanding and applying these guidelines is essential for ensuring that conductors are properly sized for their intended application. Using conductors with insufficient ampacity can lead to overheating, insulation damage, and potential fire hazards. It is also important to consider voltage drop when selecting conductor sizes. Voltage drop is the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to use larger conductors than required for ampacity alone. In summary, ampacity is a critical parameter in electrical installations determining the safe and reliable current carrying capacity of conductors. By understanding the factors that affect ampacity and applying the National Electrical Code guidelines, electricians can ensure that conductors are properly sized for their intended application, preventing overheating, voltage drop, and potential electrical hazards. Always consult the latest edition of the National Electrical Code for the most up-to-date information and requirements. The National Electrical Code is updated regularly to reflect changes in technology and best practices. Staying current with the National Electrical Code is essential for all electrical professionals. Proper grounding and bonding techniques are crucial for ensuring electrical safety and preventing electrical shock hazards. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices to trip and de-energize the circuit. Bonding ensures that all metal parts of an electrical system are electrically connected, creating an equipotential plane and minimizing the risk of shock. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding in Article 250. Understanding and implementing these requirements is essential for all electrical installations. Grounding involves connecting the electrical system to the earth through a grounding electrode. The grounding electrode provides a reference point for the electrical system and helps to stabilize voltage. The National Electrical Code specifies different types of grounding electrodes, including ground rods, ground plates, and metal water pipes. The grounding electrode must be properly sized and installed to ensure effective grounding. Bonding involves connecting all metal parts of an electrical system together, including metal conduits, metal enclosures, and metal equipment. Bonding creates an equipotential plane, which means that all bonded metal parts are at the same electrical potential. This minimizes the risk of shock by preventing voltage differences between metal parts. The National Electrical Code specifies different methods for bonding, including bonding jumpers, bonding screws, and bonding bushings. Bonding jumpers are used to connect metal parts that are not directly connected. Bonding screws are used to connect metal parts to enclosures. Bonding bushings are used to connect metal conduits to enclosures. Proper grounding and bonding are essential for preventing electrical shock hazards. Electrical shock occurs when a person comes into contact with an energized conductor on a grounded surface. If the electrical system is properly grounded and bonded, the fault current will flow through the grounding path, causing the overcurrent protective device to trip and de-energize the circuit before a person can be injured. In addition to preventing electrical shock hazards, grounding and bonding also help to protect electrical equipment from damage caused by voltage surges and lightning strikes. Voltage surges and lightning strikes can cause high voltages to appear on electrical systems, which can damage sensitive electronic equipment. Proper grounding and bonding can help to dissipate these surges and protect equipment from damage. The National Electrical Code provides specific requirements for grounding and bonding in different types of electrical systems, including residential, commercial, and industrial systems. These requirements vary depending on the voltage, current, and type of equipment in the system. It is essential to consult the National Electrical Code and follow its requirements for grounding and bonding in all electrical installations. In summary, grounding and bonding are critical aspects of electrical safety, preventing electrical shock hazards and protecting electrical equipment from damage. By understanding and implementing the National Electrical Code requirements for grounding and bonding, electricians can ensure the safe and reliable operation of electrical systems. Always consult the latest edition of the National Electrical Code for the most up-to-date information and requirements. The National Electrical Code is updated regularly to reflect changes in technology and best practices. Staying current with the National Electrical Code is essential for all electrical professionals. Always refer to the most up-to-date version of the National Electrical Code for the most accurate information.